Jai Hind everyone. Today I'll be taking the topic of process synchronization in operating system. You all must be aware of the topic process, the term process. And process synchronization is the coordination of execution of multiple processes in a multi-process system to ensure that they access shared resources in a controlled and predictable manner. It aims to resolve the problem of race conditions and other synchronization issues in a concurrent system. Now, what is a process? A process is a program in execution. You all must know that. And what is process synchronization? It is a coordination of execution between multiple processes in a multi-process system to ensure that they access shared resources in a controlled and predictable manner. It aims to resolve the problem of race conditions and other synchronization issues in a concurrent system. The main objective of process synchronization is to ensure that multiple processes access shared resources without interfering with each other and to prevent the possibility of inconsistent data due to concurrent access. So what does this term process synchronization aims at? The main objective is to ensure that multiple processes are accessing shared resources without interfering with each other, and it prevents the possibility of inconsistency which can occur due to concurrent access of resources. To achieve this, various synchronization techniques such as semaphores, monitors and critical sections are used. In a multi-process system, synchronization is necessary to ensure data consistency and integrity and to avoid the risk of deadlocks and other synchronization problems. Now, process synchronization is an important aspect of modern operating system and it plays a crucial role in ensuring the correct and efficient functioning of multi-process systems. See, when there is a multi-process system, synchronization will be needed so that it ensures that the data consistency is maintained and integrity is maintained. And to avoid the risk of deadlocks, other synchronization problems, we use synchronization. Now, process synchronization is an important aspect of modern operating systems and it plays a crucial role in ensuring the correct and efficient functioning of multi-process systems. On the basis of synchronization, processes are categorized as one of the following two types: independent process and the other one is cooperative process. Now, the independent process is the process where the execution of one process does not affect the execution of other process. While cooperative process is a kind of process which can affect or be affected by other process executing in the system. Process synchronization problem arises in the case of cooperative process, also because resources are shared in cooperative processes. Now, since as you can understand that independent process is when independent process is taking place, then the execution of one process will not affect or get affected by the execution of other process. But when in case of cooperative process, a process can affect and it will be affected by other processes executing in the system. One process, the execution of one process will affect the execution of the other process. Now, process synchronization problem arises in the case of cooperative process, also because resources are shared. Since the resources are shared in a cooperative kind of process, then the process synchronization problem arises. Now, what happens in a race condition? When more than one process executing the same code or accessing the same memory or any shared variable, in that condition, there is a possibility of that the output or the value of the shared variable is wrong. So, for that all the processes doing the race to say that my output is correct, this condition is known as race condition. Several processes access and process the manipulations over the same data concurrently. Then the outcome depends on the particular order in which the access takes place. A race condition is a situation that may occur inside a critical section. This happens when the result of multiple thread execution in the critical section differs accordingly to the order in which the threads execute. Race conditions in critical sections can be avoided if the critical section is treated as an atomic instruction. Also, proper thread synchronization using locks or atomic variables can prevent race conditions. Now, what is a race condition? When more than one process is executing in the same code, or more than one processes are accessing same memory or any shared variable. So, in that case, multiple manipulations are being performed on the same data. So, there what happens, that inconsistency arises, which leads to the situation which we term as race condition. A race condition is a situation that may occur inside a critical section. Now, you all must be aware of critical section. Critical section is that section of the code where all the shared variables are present. Now, when manipulations are performed on the same shared data, then it leads to race condition because we get inconsistent output. Now, what is a critical section problem? A critical section is a code segment that can be accessed by only one process at a time. Okay. Now, the critical section contains several shared variables that need to be synchronized to maintain the consistency of data variables. So, the critical section problem means designing a way for cooperative processes to access shared resources without creating data inconsistencies. What happens? Why do we call it a critical section problem? A critical section is a code segment which can be accessed by one process at a time. Only one process can access the critical section at a time. This critical section contains what? Shared variables that needs to be synchronized to maintain the consistency of data variables. So, the critical section problem means designing a way for cooperative processes to so that you can access shared resources without creating data inconsistencies. See, this is the example of your critical section. Now, this is the part of code where this is the entry section where you enter the code of the code in the section through the entry section. Then this is your exit section and this is your remainder section. Okay. So, this is your do while loop, and here all the manipulations or all the data are performed. In the entry section, the process requests for entry in the critical section. What happens in the entry section? The process will request for entry in the critical section. Any solution to the critical section problem must satisfy three requirements. The first one is mutual exclusion. If a process is executing in its critical section, then no other process is allowed to execute in the critical section, which means that only one process can access the critical section at a time. Now, progress. If no process is executing in the critical section and other processes are waiting outside the critical section, then only those processes that are not executing in the remainder section can participate in deciding which will enter the critical section next, and the selection cannot be postponed indefinitely. See, if the critical section is empty, which means that no process is executing the critical section, any other process which was waiting outside the critical section, then only those processes that are not executing in their remainder section can participate in deciding which will enter the critical section, and the selection cannot be postponed indefinitely. Now, bounded waiting. A bound must exist on the number of times that other processes are allowed to enter their critical section. After a process has made request to enter its critical section and before that request is granted. It cannot happen that only some process keep entering the critical section and keep accessing it. Then to control that kind of situation, a bound must exist on the number of times that other processes are allowed to enter the critical sections. Now, what is Peterson's solution? Peterson's solution is a classical software-based solution to the critical section problem. In Peterson's solution, we have two shared variables. First one is Boolean flag, which is initialized to false. Initially, no one is interested in entering critical section. We keep this Boolean flag at false initially because this signifies that no process is interested in entering the critical section. Then the other shared variable is turn, the process whose turn is to enter the critical section. Now this is your Peterson's solution. Let me explain it, break it down to you. This is your do while loop. This is your flag which has been, flag I which has been set to true. Turn has been set to j, which is an integer kind of variable. While flag j and turn equals to j, this loop will continue executing until this condition is true. Then when the process has entered critical section, it has executed in the critical section, then the flag will be set to false. Then it will enter the remainder section, and then this loop will continue, keep continuing until the while condition is true. Now Peterson's solution preserves all three conditions. The three conditions are mutual exclusion. What does mutual exclusion say? Mutual exclusion says that only one process can enter the critical section at a time. So mutual exclusion is assured as only one process can access the critical section at any time. Progress is also assured as a process outside the critical section does not block other processes from entering the critical section. Bounded waiting is preserved as every process gets a fair chance. Every process enters the critical section at a time, and it will remain there until it has been completely executed. Now what are the disadvantages of Peterson's solution? It involves busy waiting. In the Peterson solution, the code statement while flag j and turn equals to j is responsible for this. Busy waiting is not favored because it wastes CPU cycles that could have been used to perform other tasks. It is limited to 2 processes. Peterson's only 2 processes can be executed at a time in a Peterson solution. These are the disadvantages of Peterson solution. Now, and Peterson's solution cannot be used in modern CPU architectures. You cannot use these kind of solutions in the modern CPU architectures. Now, what is a semaphore? A semaphore is a signaling mechanism, and a thread that is waiting on a semaphore can be signaled by another thread. A semaphore is a signaling mechanism, and it is a thread that is waiting on a semaphore can be signaled by another thread. This is different than a mutex, as a mutex can be signaled only by the thread that is called the wait function. Mutex is your mutual exclusion lock, okay, and it is signaled by the thread which is called wait function. A semaphore uses 2 atomic operations, wait and signal, for process synchronization. A semaphore is an integer variable which can be accessed only through 2 operations. One is wait and the other one is signal. There are 2 types of semaphores, binary semaphores and counting semaphores. Now what is a binary semaphore? Binary semaphore, they can be only either 0 or 1, as the name suggests. It is a binary kind of semaphore. So automatically the value will be either 0 or 1. They are also known as mutex locks, as the locks can provide mutual exclusion. All the processes can share the same mutex semaphore that is initialized to 1. Then a process has to wait until the lock becomes 0. Then the process can make the mutex semaphore 1 and start its critical section. When it completes its critical section, it can reset the value of the mutex semaphore to 0, and some other processes can enter its critical section. The other is counting semaphore. So I hope it's clear that what is binary semaphore. Binary semaphore is a kind of semaphore which can be either 0 or it can be 1. They are also known as mutex locks. as the locks can provide mutual exclusion, these locks are the kind of locks which can provide mutual exclusion. All the processes can share the same mutex semaphore that is initialized to 1. Then a process has to wait until the lock becomes 0. Then only the process can make mutex semaphore 1 and start its critical section. Okay. Now coming back to counting semaphores. What are counting semaphores? They can have any value and are not restricted over a certain domain. Counting semaphores can have any kind of value and they are not restricted over a certain domain. They can be used to control access to a resource that has a limitation on the number of simultaneous accesses. The semaphore can be initialized to number of instances of the resource. Whenever a process wants to use that resource, it checks if the number of remaining instances is more than 0. That is, a process has an instance available. Then the process can enter its critical section, thereby decreasing the value of the counting semaphore by 1. After the process is over with the use of the instance of the resource, it can leave the critical section, thereby adding 1 to the number of available instances of the resource. Now, what are the advantages and disadvantages of process synchronization? Let's first read about the advantages. Now, the most important advantage of process synchronization is that it ensures data consistency and integrity. It avoids race condition. It prevents inconsistent data due to concurrent access. It supports efficient and effective use of shared resources. And what are the disadvantages of process synchronization? It adds overhead to the system. It can lead to performance degradation. It increases the complexity of the system. It can cause deadlocks if not implemented properly. Now, let's study about the introduction of deadlock in the operating system. You all must be aware of the term deadlock. What is deadlock? A process in operating system uses resource in the following way. It requests a resource, it uses the resource, and then it releases the resource. A deadlock is a situation where a set of processes are blocked because each process is holding a resource and waiting for another resource acquired by some other process. Let's understand with the help of this example. Consider an example when two trains are coming toward each other on the same track. And there is only one track. None of the trains can move once they are in front of each other. A similar situation occurs in operating system when there are two or more processes that hold some resources and wait for resources held by others. For example, in the below diagram, process 1 is holding resource 1 and waiting for resource 2 which is acquired by process 2, and process 2 is waiting for resource 1. See, let's consider let's take another example. Suppose you go to a shop, okay, and then you want to buy 2 packets of Maggi, okay. Now, the shopkeeper asks you to give 48 rupees or whatever is the cost of your product or Maggi. And you say that first you give me my Maggi and then I will pay you. But he disagrees and he says, no, you first give me the amount which is amount of the Maggi, and then I will give you your product or Maggi. So, this kind of situation, neither of you are agreeing to the same condition. This is termed as deadlock. Okay. See, through this example, you can see that process 1 already has a resource 2, right? But, resource 1 is assigned to process 1, okay? But it is waiting for which resource? Resource 2, right? And same thing is happening with process 2. Process 2 is waiting for resource 1, but it already has resource 2. And it is waiting for which resource? Resource 1. So, this kind of condition is a deadlock condition, and this is a diagram of a deadlock. Now, examples of deadlock. Suppose the system has two tape drivers, P1 and P2. Each hold one tape driver and each needs another one. Semaphores A and B initialize to 1, P0 and P1 are in deadlock as follows. P0 executes wait A and preempts. P1 executes wait B. Now P0 and P1 enter in deadlock. You all must be aware of the term preemption and non-preemption. What do you mean by preemption? Preemption is the kind of process which can be preempted, which can be released. Okay, and non-preemption happens when a process does not leaves the critical section until it has completely been executed. Now suppose there is a system which has two tape drives, one is P1 and one is P2. Now each is holding on to one tape drive and each needs another one. Semaphores A and B are being initialized to 1. P0 and P1 are the semaphores in deadlock. Now P0 is executing wait A and then it will preempt. Now P1 will execute wait B. Now P0 and P1 will enter in the condition of a deadlock. See, P0 is in a waiting A and P1 is in wait B. Similarly, P0 is in wait B and P1 is wait A. This is also an example of a deadlock. Deadlock occurs if both processes progress to their second request. Now, deadlock can arise if the following 4 conditions hold simultaneously. For a deadlock to happen, these 4 conditions need to be satisfied, and this is a very important question from the exam point of view. The one is mutual exclusion. 2 or more resources are non-shareable. Only one process can use a resource at a time. Second is hold and wait. A process is holding at least one resource and waiting for resource. A process which is already holding a resource and it is waiting for another resource which is being held by another process. So this is termed as hold and wait. And what is mutual exclusion? When 2 or more resources which are shareable, but one process can use a resource at a time. The third one is no preemption. A resource cannot be taken from a process until the process releases the resource. Fourth one is circular wait. A set of processes waiting for each other in circular form. So these are the 4 conditions which need to happen for necessary conditions of deadlock which need to happen for a deadlock to arise. Now, how can you handle deadlock? Methods for handling deadlock. There are 3 ways to handle deadlock. The first one is deadlock prevention or avoidance. Prevention. The idea is to not let the system into the deadlock state. You should prevent the deadlock from happening. This system will make sure that above mentioned 4 conditions will not arise. These techniques are very costly, so we use this in case where our priority is making a system deadlock free. One can zoom into each category individually. Prevention is done by negating one of the above mentioned necessary conditions for deadlock. Prevention can be done in 4 different ways. The first one is eliminate mutual exclusion. Second one is solve, hold and wait. Third one is allow preemption. Fourth one is circular wait. Now avoidance. Avoidance is a kind of futuristic. By using the strategy of avoidance, we have to make an assumption. We need to ensure that all information about resources that the process will need is known to us before the execution of the process. We use Banker's algorithm, which is turn a gift from Dijkstra's to avoid deadlock. In prevention and avoidance, we get the correctness of data, but performance decreases. In the first phase, we examine the state of the process and check whether there is a deadlock or not in the system. If found deadlock in the first phase, then we apply the algorithm for recovery of the deadlock. In deadlock detection and recovery, we get the correctness of the data, but performance decreases. Recovery from deadlock, manual. How can you recover from a deadlock which has already happened? To recover from a deadlock, there should be mutual intervention. When a deadlock is detected, one option is to perform the operator and let them handle the situation manually. While this approach allows for human judgment and decision making, it can be time consuming and may not be feasible in large scale systems. Automatic recovery, an alternative to enable the system to recover from the deadlock automatically. This method involves breaking the deadlock cycle by either aborting processes or preempting resources. Let's delve into these strategies in more detail. How can you recover from deadlock process termination? First is abort all deadlocked processes. Second step is to abort one process at a time. When you abort all deadlock processes, this approach breaks down the deadlock cycle, but it comes at a significant cost. The processes that were aborted may have executed for a considerable amount of time, resulting in the loss of partial computations. These computations may need to be recomputed later. Now, when you abort one process at a time, instead of aborting all deadlock processes simultaneously, this strategy involves selectively aborting one process at a time until the deadlock cycle is eliminated. However, this incurs overhead as a deadlock detection algorithm must be invoked after each process. Termination to determine if any processes are still deadlocked. Now, factors for choosing the termination order. How can you terminate the processes to prevent deadlock? There should be some factors. The first one is the process's priority. On which priority is the process? Completion time and progress made so far. Third is resources consumed made by the process. Resources required to complete the process. Number of processes to be terminated, and the process type, interactive or batch. Recovery from deadlock. Now, in case your deadlock has already happened, how can you recover from a deadlock? The first part is step is to resource preemption. Selecting a victim. Resources preemption involves choosing which resources and processes should be preempted to break the deadlock. The selection order aims to minimize the overall cost of recovery. Factors considered for victim selection may include the number of resources held by a deadlocked process and the amount of time the process is consumed. Rollback. If a resource is preempted from a process, the process cannot continue its normal execution as it lacks the required resource. Rolling back the process to a safe state and restarting it is a common approach. Determining a safe state can be challenging, leading to the use of total rollback where the process is aborted and restarted from scratch. Starvation prevention. To prevent resource starvation, it is essential to ensure that the same process is not always chosen as a victim. If victim selection is solely based on cost factors, one process might repeatedly lose its resources and never complete its designated task. To address this, it is advisable to limit the number of times a process can be chosen as a victim, including the number of rollbacks in the cost factor. Deadlock ignorance. If a deadlock is very rare, then let it happen and reboot the system. This is an approach that both Windows and Unix take. We use the ostrich algorithm for deadlock ignorance. In deadlock ignorance, performance is better than the above two mentioned methods, but the correctness of the data. Now, one more thing that you should know about is a safe state. What is a safe state? A safe state can be defined as a state in which there is no deadlock. This question will be asked in your examination, so please be clear about it. A safe state is defined as a state in which there is no deadlock. It is achievable only if a process needs an unavailable resource. It may wait until the same has been released by a process to which it has already been allocated. If such a sequence does not exist, it is an unsafe state. I will be taking your next lecture of operating system based on one of a synchronization algorithm or solution to the critical problem. Okay, thank you so much.